All right, let's continue on by discussing optical activity, which is a commonly used way to differentiate between stereoisomers, namely enantiomers. So first, a little bit about light. It says to get light waves that travel in only one plane, we have to pass them through a polarizing filter. So normally, if you have light shining, it oscillates in all directions perpendicular to the plane of travel, right? You should be aware that light is an electromagnetic wave. Anyhow, so if we have light that oscillates in all directions, what we can do is this is like, let's imagine we have a light bulb over here. So here's our light bulb. Okay, it looks like this. Okay. And then it's shining light, which is oscillating in every direction. And then we pass it through a polarizing filter. So this is a polarizing filter. And it works the exact same way that polarized sunglasses work. And so if we have the polarizing filter so that the slits are aligned, maybe I should use a different color here, so that the slits are aligned vertically like this, the only light wave that's going to be able to pass through is going to be this one here, which is in line with the slits, right? Because it's going perfectly vertical like that. So that's what polarized light is. And so after you pass that through a polarizing filter, and you can see the person has a second filter lined up here, and it's again aligned in the exact same orientation as the polarized light. So this is the plane, we call this plane polarized light, okay? Then the viewer can see the light. But if the viewer was to take the second polarizing filter and rotate it, so you can see they turned it 90 degrees here, they went from here to here and rotated it 90 degrees. Well, now the slits are going not opposite, but they're going horizontally now. And so it's going to block that plane polarized light from passing through. So that's what a little bit about plane polarized light. And if you're wondering, well, what does this have to do with a molecule? What it's got to do with a chiral molecule is this. It says compounds can actually take plane polarized light, okay, and they can rotate it. So they can rotate the plane polarized light. And when they do, we say the compound is optically active. So going back here, the idea is this, is that if you shine this plane polarized light through a chiral compound, the chiral compound can rotate the plane polarized light clockwise or counterclockwise, depending on the compound. And if you're wondering, well, how would you do that? Good question. Okay, you would do that using an instrument called a polarimeter. So here we have our light source. It's a sodium lamp. So sodium lamp, and we use what's called the D line of sodium. That's neither here nor there. But anyhow, you can see that the light is oscillating in all directions perpendicular to the direction of travel. It's passed through the polarizing filter, and so the light is only coming out, vertically like this. Okay, so then what you do is you take your compound and you dissolve it in an organic solvent. So inside the polarimeter tube, you have your organic compound dissolved in a solvent. Okay, so you have a solution of your compound. And then you shine the plane polarized light through the solution of the compound. And the idea is that the molecule that's in solution is going to cause the plane polarized light to rotate in one direction, clockwise or counterclockwise. And if you're wondering, well, how do you figure out how much it's rotated? Well, what you do is you adjust the second polarizing filter that you're going to be looking at on the other end. So here's your eyeball looking through here, and you adjust this polarizing filter so that the lines align exactly with how much the molecule has rotated the plane polarized light so that you can view the light. And then you measure the degree of rotation. So we say the optical rotation occurs at so many degrees. Is it rotated 90 degrees or 15 degrees or minus 15 degrees, et cetera, et cetera. So enantiomers, and just follow along with me here. Let's go through every bullet point on here. First one, enantiomers are going to rotate plane polarized light in equal amounts, but in opposite directions. So let's say you have an R compound that rotates plane polarized light positive 15 degrees. The S compound is going to rotate it negative 15 degrees. So it's going to be equal in amount, but opposite in the direction. The second point says the degree to which the light is rotated in the sample depends on the concentration and path length. And then it says the standard optical rotation measurements occur with 1 gram of compound dissolved in 1 ml of solution with a path length of 10 centimeters for the light. Look, you don't need to know anything about those 2 points there. I'm not going to ask you anything about that. The only thing I would really tell you is that when we measure optical rotation, we report the temperature up at the top. The temperature is usually 20 degrees Celsius. And then for the wavelength, we usually put D because we use the D line of sodium. I'm not going to ask you to do any calculations with respect to optical activity. All I want you to know is this. If you have one enantiomer that rotates plane polarized light, like our 2-bromobutane, it rotates it by negative 23.1 degrees. Well, then the enantiomer is going to rotate it to positive 23.1 degrees. All right, that's all I want you to know. So positive and negative refer to clockwise and counterclockwise, respectively. And RNS refer to configuration of the chiral center. Look deep into my eyes or listen to my voice very, very carefully here. There is no connection, none, between R and S and positive and negative. Okay, if an R compound rotates plane polarized light minus 23.1, maybe another R compound, maybe R2 chlorobutane rotates it positive. You know, there's no correlation between the two. So don't try to draw a connection that doesn't exist, because it doesn't exist. And also, you cannot predict optical rotation. Can't be predicted at all. It has to be measured directly. It says here, we call the positive rotation, so counterclockwise, we call that dextrorotatory, and negative, we call that, or counterclockwise, we call that levorotatory. So check this out. The optical rotation, as to whether it's dextrorotatory or levorotatory, it's even dependent on temperature. The name isn't important. You'll learn that in biochemistry, or maybe at the end of organic too. We'll talk about this compound. But anyhow, you see that this compound has a levorotatory optical rotation at room temperature, but it goes dextrorotatory at 100 degrees Celsius. So again, I can't stress this enough. There's always somebody who tries to draw this correlation, but there is no correlation between R and S and levo and dextrorotatory. There is no correlation whatsoever. It cannot be predicted in any way at all. The next thing here that I would want you to know, okay, so again, the magnitude, direction cannot be predicted. It has to be measured. The only thing that we can say for sure is if you have a racemic mixture. So a racemic mixture is a 50-50 mixture of two enantiomers, R and S. So let's go back here. Let's imagine you had these two enantiomers, okay? If you have a racemic mixture of these two enantiomers, how is it going to affect the rotation of plane polarized light? Well, one's going to rotate at negative 23.1, and the other one's going to rotate at positive 23.1. So what do they do to each other? Can anybody make a guess? Go with your gut. What are they going to do if they're equal and opposite? Starts with C, ends with ancel. That's right. They cancel each other out. So when you have a racemic mixture, okay, you get, so I'll highlight it in yellow. A racemic mixture gives you an optical rotation of 0 because the two enantiomers cancel each other out. Rotation of a racemic mixture is 0. There you go. The whole thing about enantiomeric excess, I'm not going to ask you any questions about this, so I'll even write it in my slides. The whole thing here in excess, which we call that EE, I'll put here, will not ask. So you don't have to worry about any questions that deal with enantiomeric excess. I don't cover that. And so I'm not going to ask you to do any of these kind of calculations here whatsoever, okay? I'll even write it here on the slide for you again. Will not ask you this, okay? You're off the hook. For enantiomeric excess, I will not ask you about it again for the third time. Will not ask enantiomeric excess. So if you're wondering, well, what do I need to know? Okay, this is the basics. Okay, you need to understand what polarized light is. You need to be able to understand that a chiral compound is going to rotate plane polarized light in one direction. The enantiomer is going to rotate it an equal amount, but the opposite direction. You can't predict positive or negative. You can't predict that. You should know what optically pure means. That means just a pure enantiomer. So pure enantiomer. Enantiomeric excess, you should know that it just means you have one enantiomer in a greater quantity than the other. It's literally what it says, enantiomeric excess. And then racemic mixture, again, that's a 50-50 mix of two enantiomers. enantiomers. Okay, enantiomers. There we go. All right, so that's the crux of what you need to know from section 5.4. Well, let's turn our attention to section 5.5, which deals with something called a diastereomer. So we've covered enantiomers in detail. And if you remember, enantiomers were what? They were non-superimposable mirror images, right? That's a definition you have to have memorized. And if you back it up even further, we were talking about constitutional isomers and stereoisomers, and enantiomers are one type of stereoisomer, but there's a second type of stereoisomer that we need to cover that we haven't covered yet, and that is diastereomers. So diastereomers are molecules with the same connectivity, different arrangement of atoms, but they're not mirror images of each other. Okay, so diastereomers, not mirror images. The simplest possible example I could give you would be cis and trans compounds. If you had this compound as a trans compound and this compound is a cis compound, these two compounds are 2-butene. They're cis and trans, but they're not mirror images of each other, are they? And are they stereoisomers? Yes. So since they're stereoisomers, but they're not enantiomers, these two would be considered to be diastereomers, right? And we're going to look at several examples of diastereomers. All right. So there you go. Cis and trans 2-butene. What do you know? It was on the next slide. That these are not mirror images of each other, but again, they are stereoisomers. You agreed with me on that earlier, and therefore they are diastereomers. So recall that two enantiomers have identical physical properties, but diastereomers, they're not going to pack in the same way, are they? If I have two molecules of this compound versus two molecules of this compound, they're not going to pack in the same way whatsoever, and therefore they're going to have different physical properties. They're going to have different, melting points, boiling points, etc., densities, etc. All right. So now that we've defined what a diastereomer is, let's take a look at a cyclohexane molecule that has three different substituents. So if you're looking at this and going, don't worry, we're going to go over it very slowly here, okay? So let me show you. If I just zoom in to these two compounds here. Okay, let's just focus on one compound to start with. We'll just focus on this guy here. Okay, every group is pointing up. You have a hydroxyl that's pointing up, a methyl pointing up, and a chlorine pointing up. So if you designate the stereocenters here, you have 1R, 2R, 3S. Okay, so 1R, 2R, 3S. Now, if I flip every wedge in this molecule in the box, if I flip them all to a dash, what's the relationship between these two molecules that are shown here in the green box? You flipped every single stereocenter. What's the relationship between these two molecules here? Could anybody tell me the relationship between these two? I flipped every wedge to a dash. What do I get when I invert every single stereocenter? Yes, they're mirror images, but keep going. What would be the term I would use to describe these two compounds? Exactly. These two compounds are enantiomers of each other. They're non-superimposable mirror images of each other, right? There you go. So these two compounds are enantiomers. I flipped every wedge to a dash. In other words, I took every R center and I turned it to an S. So I took R, converted it to S, R converted it to S, and S and converted it to R. So if you invert every R and S, what do you get? The enantiomer. Give me a thumbs up if you're with me on that. That these two compounds are enantiomers, all I did was invert every single stereocenter. Okay, let's go over to the green box next to it. What's the relationship between these two molecules in here? Could anybody unmute their mic or type it in the chat? What's the relationship between these two molecules? Are they enantiomers again? Yes, Sean, they are, aren't they? Right, because how does he know that? I took every wedge, made it a dash. I took the dash, I made it a wedge. And if you're like, well, I don't even need to have the structure of the molecule. I can see that they flipped every R to an S. And there you go. Every R has been inverted to an S. So there you go. These two molecules are enantiomers of each other. So this is a pair of enantiomers. Let's keep going, but a little faster. We'll go down here. Would these two compounds be enantiomers? Yes or no? and it's not a trick. I hate fooling people. In fact, I don't do it. Yes, these are enantiomers, aren't they? Enantiomers. No arguing that, right, Sean? Yes, beautiful. Kiana, excellent. What about, again, last time? I promise we'll stop after this. What's the relationship between this pair? Yes, they're enantiomers, right? I inverted every stereocenter. Thanks, Sean. And thank you for your patience, okay? But you can imagine why I'm doing this, right? It's on purpose, okay? So all of those pairs of compounds in there, in those green boxes, they're all pairs of enantiomers. Everything is a pair of enantiomers. Okay, so now that we've settled that, let's try something different. You see the compound that I have in the blue box or the blue square? I'm going to circle or put this compound in a red box. Okay, you can rent it for to watch it or something. Kidding. All right, so if I compare these two compounds, the one in the blue box and the one in the red box, what's the relationship between those two? So I'm going to guide you through the answer. Are they enantiomers? Yes or no? Those two compounds? Definitely not. Okay, they're not enantiomers. Okay, they're not identical. They're not enantiomers. Are they stereoisomers? Are the atoms, did they have a different orientation in space? Yes, absolutely, right? You see that the hydroxyl is going up, going up, going up for the methyl, going up. Uh-oh, but this chlorine is up and this chlorine is down. So they have the same connectivity, but they have a different arrangement in atoms in space. Therefore, they are stereoisomers, but they're not enantiomers, and ergo they must be. What's the definition of these two compounds? They are second cousins twice removed. No, thanks, Hannah. They're diastereomers, aren't they? Exactly. These are diastereomers. Diastereomers. Stereomers. Right, Hannah? Those are diastereomers. So that means that the compound in the blue box is a diastereomer of the one in the red box. It's a diastereomer of this, 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 this. So to rehash, the compound in the blue box has one enantiomer, but it has 6 diastereomers. All right, and we could do the exact same treatment for any of the molecules in here, okay? We could put a box, let's just delete some of this action here, right? Let's just pick one compound at random. Let's pick this compound here. If I put this compound in a box, okay, that compound has one enantiomer. It's this compound here, but it is a diastereomer of this compound, this compound, this one, this one, this one, and this one. So it's got one enantiomer and 6 diastereomers. Give me a thumbs up if you follow me on that. You're probably thinking, oh, shoot, don't make me draw all those, or something, which is fine for you to think that. But it's more about the relationship. Good. So it says there's 3 stereocenters, so there's 8 possible stereoisomers. Remember, we said 2 to the power of n, and so we have 2 to the power of 3, which gives us 8 possible stereoisomers. And we just looked at the relationships between all of them. So one more time before I turn the page. Diastereomers, stereoisomers, but not mirror images of each other. That's all the definition is. Nothing more than that. So I've already gone over the whole formula to determine the maximum number of stereoisomers. This one is kind of a fun thing. I shouldn't say fun in a chemistry class, but anyhow, it's kind of an interesting thing to look at. This is a molecule of cholesterol. I'm sure that many of you have studied the phospholipid bilayer in biology class and have seen cholesterol and its part in cell membranes and all that kind of stuff, and steroid synthesis, etc., and hormone synthesis. But anyhow, I digress. It has a total of 1, 2, 3, 4, 5, no, 1, 2, 3, 4, 5, 6, 7, 8 stereocenters in cholesterol. And so if you were to calculate the maximum number of stereoisomers, you have to do 2 to the power of 8, which you probably don't know off by heart. You could figure it out in your head, but it gives you 256. So that means that cholesterol has one enantiomer, okay? But how many diastereomers would cholesterol have? Right? If there's 256 possibilities, one of them is cholesterol, one of them is its enantiomer, it would have 254, right? Because one of the stereoisomers is cholesterol, one would be its enantiomer, and so it would have 254 Diastereomers. There you go, my friends. So, the reason, I mean, I guess David Klein put this in the textbook because he thought it was interesting or just to prove it. What's interesting to me about this is if you think of that nature, we can make cholesterol, and if there's 256 different stereoisomers that we could come up with, 255 of them being the wrong one. I mean, it's pretty remarkable that nature is able to make the correct one over and over and over. So, chiral synthesis is difficult. Can you imagine installing 8 chiral centers? That sounds like my idea of hell. So let's, with that in mind, let's take a look at a practice problem. Okay, so let's take a look at 5.19. We'll start with question A, and we'll get Eric to answer this for everybody. Eric, what's the relationship between these two, or anybody? Thanks, Eric. They're enantiomers. I like it. You can handle the pressure in the enantiomers. How did you know that, Eric? Keep going. How did you know? Give me your rationale. Yeah, they flipped every wedge to a dash and every dash to a wedge. Exactly. So those two are mirror images. Non-superimposable. Yes, exactly. I see that everybody answered it correctly. All right. So those two are enantiomers. Let's go to the next one. Da, 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 Let's see who's there. I can see Ashley, Kiana, Katana. There you go. Thanks, Katana. Awesome. These are diastereomers. Can't argue with that. Diastereomers. Yep. Because they have a different arrangement of the atoms in space. One is a cis. This is a cis compound. This one is a trans compound. Right, same connectivity, just different orientation of atoms in space. And so these would be diastereomers, absolutely. The next one is actually kind of tricky, okay? Because they didn't put the methyl groups here. The methyl groups here are not in the same plane. You got two options here with this one. And man, it's a tough problem. By the way, this is like your MCAT kind of problem. This is the kind of junk they love to ask on an MCAT. Okay, is what's the relationship between these two? You've got two options. Okay, number one option is you could rotate this. You could rotate this bond to put the chlorine in the plane with this chlorine. So if you did that, just let me draw it for you here quickly. You would end up with something, and you have to be really good at rotating things in your mind. Not that Mr. Dion is God's gift to it or anything, but if you did that, you end up with the chlorine out here, and you end up with a methyl group in the back, like this. So my question to you is, what's the relationship between these two compounds? Could anybody tell me what the relationship is between these two? Now that I've rotated the chlorine into the plane. They're not enantiomers. No, because one stereocenter is the same, right? This one is the same, but this one, the second one, is different, right? So they must be diastereomers. Yes, thanks, Sean. Good, so we'll put here diastereomers. That's one way of doing it. And actually, now that I think, I like this way the most. If you can rotate the molecule in your mind, this is the way to go. The other way, which is more painful, but it's foolproof, it's going to work 100% of the time, is assign every stinking stereocenter in the molecule in both of them and then compare them. Okay, so let's do it. Is this an R or an S? Well, let's see. We've got a hydrogen in the back. So this is 1, this is 2, this is 3, this is 4. So we go, son of a gun. Did I put Mr. Dion? You need more coffee, man. This is our 1, this is our 4. There we go. This is our 2, this is our 3. So we're going to go like this. So that stereocenter is an R stereocenter. So let's erase all this stuff. So this stereocenter is R. Let's do this one here. I'll do it in blue. We have a hydrogen in the back. Okay, so this is 4, this is 1, this is 2, this is 3. We go like that. That's clockwise, and so that's an R stereocenter. So I'll erase all this, and we'll put here that this stereocenter is also R. So we have RR for the first one. And then for the second one, well, the first one has to be R because that hasn't changed. And then if we look at the second one, So we have a hydrogen going in the back. So this is group number 4. This is group number 1. This is group number 2. And this is group number 3. So we go like this. And that is going backwards. So it's S. We saw that. This is an S stereocenter. So we have RR and RS. So therefore, they must be diastereomers. Again, that one's more painful. It takes more work, but it'll work. It's always going to work. You won't make a mistake as long as you know your Kahn-Ingold Prelog rules. All right, there you go. So somebody asked me a question. It says, without redrawing or repositioning it in your mind, would it be wrong just to say that you have two groups switching planes between the stereoisomers? Let's see. Yeah, you could do that too, Sean. Right. So yeah, you could say the second stereocenter, since you have the chlorine switching and the methyl switching places, yes, you could say that the stereochemistry reverses. That would work too. Yeah. Yeah, that'll totally work. The only, it just, sometimes it gets tricky. I don't know. But yeah, your point is definitely valid, and that would definitely work. Yeah, absolutely. All right, so let's go back. Look at something interesting here. Where was it? Oh, I'm going too far back in time. Okay, let me move forward. I wanted to show you something about. Oh, I know what I wanted to tell you was, you know, this whole 2 to the power of n rule. This whole rule here. Well, that says maximum number of stereoisomers. Notice it doesn't say total. Okay, it says that's the maximum. Sometimes you're actually going to get less than the maximum number of stereoisomers. And when does that happen? It happens when you have a plane of symmetry in the molecule. And let me show you what I mean by that. So check this out. So now we're going to get into symmetry and chirality. By the way, this is a topic that can just get so deep. In fact, the whole stereochemistry thing can be very, very deep topic. But we're just kind of learning the basics of it in this class. It says here that any compound with only one chiral center will be a chiral compound. Okay, cool. That's cool. Like if you have, I don't know, what was the compound we looked at before? It was this, right? R2-chlorobutane, right? One chiral center, it's a chiral compound, done. That's it. But check this out. This is where it gets kind of interesting. I was going to say confusing, but I stopped myself. With more than one chirality center, a compound may or may not be chiral. It may have a plane of symmetry. So read very carefully, okay? This is fine print. It's got more than one chirality center. So it does have chiral centers in the molecule, but the molecule itself, it says the compound may not be chiral. So what that means is that even though the molecule has chiral centers in it, it doesn't rotate plane polarized light. Okay, so does not rotate plane polarized light. So it has no optical rotation. So why would that be? Let's take a look at these two diastereomers here, trans and cis 1,2-dimethyl cyclohexane. So they both have two chiral centers. Those are two chiral centers, and these are two chiral centers. But it turns out that one of these molecules is not chiral. Okay, I'm not saying it doesn't have a chiral center. They both have two chiral centers, but I'm saying the molecule is not chiral. The whole kit and caboodle, one of these is not chiral. It's this one. And what does that mean? That the molecule itself, when you put it in solution and shine plane polarized light through it, it doesn't rotate the plane polarized light. So let's take a looky. It says the trans isomer is chiral, but the cis isomer is not. Why? Because here's the definition. If a molecule has a plane of symmetry, not an axis of symmetry, a plane of symmetry, meaning like a mirror plane, it's going to be achiral. Hopefully you can see that there's clearly a mirror plane down this molecule, that it reflects on both sides. You can see that very clearly here, okay? So if that cis isomer has a plane of symmetry, and that means it's going to be superimposable on its mirror image, and therefore it's not a chiral compound. That's one way of thinking of it. I can tell you another way that I like to think about it. If you look at this molecule here, this is a chiral center, this is a chiral center. But do you see how the two chiral centers are kind of mirror images of each other? Well, that means that one is going to rotate plane polarized light in one direction, and the other one's going to rotate it in the same amount, but in an opposite amount. And I don't know whether they're clockwise or counterclockwise. That's neither here nor there, but they're going to cancel each other out. So when you add those two things up, you get 0. So if you have a compound that's got stereocenters, but it's got a plane of symmetry, the molecule is not chiral. It doesn't mean it doesn't have chiral centers. The molecule is not chiral. So that means it has no effect on planed polarized light. So those compounds, of course, they have to have a name. We call them meso compounds, right? Not like miso soup, that's M-I-S-O. Anyhow, molecules with an even number of chirality centers that have a plane of symmetry, we call them meso compounds, okay? So cis 1,2-dimethylcyclohexane, this is a meso compound. Another way to test if a compound is meso is see if it's identical to its mirror image. If it is, it can be a meso compound. And so by definition, if you look at the bottom point here, when a compound is identical to its mirror image, it's not chiral, it's achiral. It's not going to rotate plane polarized light at all. There you go. So if we look at this compound here, okay, let's just zoom in on this guy here. It's got 2 stereocenters, right? 1, 2. So you might be tempted to say 2 to the power of 2 means I'm going to have 4 stereoisomers. Well, you do end up with this pair of enantiomers, but once you draw a diastereomer of it, this diastereomer that you see right here, I'll put it in a red box, okay? So these 3 compounds that you can see on the screen currently, those are all stereoisomers of each other. But if I flip both of those wedges to 2 dashes, these 2 compounds here are identical to each other, right? Because there's a plane of symmetry. If I take this molecule in the red box, okay, and if I draw an axis here, if I rotate this 180 degrees, I end up with the exact same thing. Okay, I end up with this compound over here. And so this compound here is a meso compound. It's got chiral centers, but it's got a plane of symmetry. So that 2 to the power of n, that gives you the maximum number of stereoisomers, but you might not always get that maximum. You might have less, like we do in this case. So a meso compound. So it says for question 5.24, draw all possible stereoisomers for each of the following compounds. Each possible stereoisomer should be drawn only once. Okay, well, let's take a look at this first compound. We've got 2 chiral centers. We've got one here and we've got one here. So what are my possibilities? I can have, we'll put like this, we'll have one methyl group going up, we'll have another methyl group going down. And I can also draw its enantiomer, where I have this methyl group going down and this methyl group going up, like this. Now, is there another possibility? If I have this methyl group going down, and then if I have these 2 methyl groups going, both of them going up. Okay, so I've deliberately made a mistake here. Could anybody tell me what my mistake is? The last 2 are the same. Exactly. Exactly. So these 2 compounds here, identical. Identical. Right? Because this compound, it's not very pretty, but this is a meso compound. And so we have a total of 3 stereoisomers. Okay. These are the stereoisomers. All right. And for the next one, we have 2 chiral centers. So it's kind of in the same vein. We would have this, where we have one hydroxyl going up and another hydroxyl group going down. Then we have this, where we have this one going down and this one going up, straight up, like that. And so these 2 compounds would be enantiomers. And then, of course, we have only one more stereoisomer. We don't have 2 more, because if you put both of the hydroxyls going up, it would be the exact same thing as if they were both pointing down, because this is a meso compound, right? We can see that there's a plane of symmetry down the molecule like that. So we end up with a total of 3 stereoisomers. Any questions about that problem? Identifying meso compounds, everything. All right. Are you ready? Let's see, we got Fisher projections. Let me go over Fisher projections with you quickly. So it won't take too long. Section 15.7. If you have a compound that has multiple chirality centers, Fisher projections can come in really, really handy. Okay, they were developed by Emil Fisher. He's the one who determined this, all the chirality centers in glucose. So if you've studied biology, and I know a lot of you have, you might have seen this in your biology textbook where they draw glucose like this. Has anybody here ever seen this before? Anywhere in their travels? So they call this D-glucose. Anybody seen this at all anywhere in a biology textbook? No, maybe not. I don't know. Anyhow, so there's 4 chiral centers in D-glucose, 1, 2, 3, 4. And so he needed a way to keep track of all these different chiral centers, and so he developed the Fisher projection. So you're probably wondering, which way are the lines pointing, if they're horizontal or vertical? And the answer is this, is that the horizontal lines are coming out towards you. So you could technically draw them on wedges. We don't, but you could, okay? And then the vertical lines, those are the dashes. I don't know why I'm using a red pen, but that didn't come out very well. Maybe I'm getting punished for using a red pen. There we go. All right. So the vertical lines are going back into the page or back into the screen, and the horizontal lines are coming out towards you. And the same thing applies here, right? All the horizontal lines are coming out towards you, right? And all the vertical lines are going back. Okay, I'm not going to draw them all in because that would be way too painful. So there you go. That's how we draw a Fisher projection. And so if you were determining the stereochemistry at a Fisher projection, so here's our chiral carbon. Right here, is this chiral carbon R or S? Well, this is going to be number 1. This is going to be number 4. Then ethyl is going to be number 2, and methyl is going to be number 3. So we go from 1 to 2 to 3 around the stereocenter, which looks like it's R. But remember that in a Fisher projection here, the hydrogen is coming out towards you. And so this compound is not an R compound. We flip it to an S. It's an S compound. Give me a thumbs up if that makes some sense to you now that you've seen it. Since the hydrogen is horizontal, it's coming towards you, so you reverse it. Good. There you go. Well, let's see here. We got all these different chirality centers and all these different sugars. And I can't name all these sugars off the top of my head, but we could try designating a chiral center or two here. We tried this molecule on the far left. If we look at this guy, our oxygen is going to be number 1. The hydrogen is going to be number 4. This carbon is attached to oxygen, oxygen, hydrogen. And this carbon is attached to oxygen, carbon, hydrogen. You can see the tiebreaker is here. And so this is going to be group number 2, and this is going to be group number 3. So we go from 1 to 2 to 3 around the chiral center. That's S. And then we reverse it again because the hydrogen is coming out in front. And so the stereocenter is R. So we'll erase all that spinach. Put here that this is an R stereocenter. And then for the second one, we follow the same kind of rationale. This is 1, this is 4. This carbon is attached to oxygen, hydrogen, hydrogen. This carbon is attached to oxygen, carbon, hydrogen. My tiebreaker is here. This is 2, this is 3. So I go from 1 to 2 to 3, which looks clockwise. So it's R, but we flip it to S because the hydrogen is coming out. And so this is an S stereocenter. So it's something that you need to practice, obviously, but that's how you designate R and S in a Fisher projection. And we'll get some practice on that in just a second here. What's really handy with Fisher projections when we study carbohydrates in organic too, it's very, very useful to determine the stereoisomeric relationships between 2 different compounds, because you can see quickly when you have a pair of enantiomers or a pair of diastereomers. It's very easy to assess without having any wedges or dashes in the compound. So that's one of the utilities of Fisher projections. So with that in mind, why don't we try a problem here? And what we'll do is we'll take a short break, and then we'll come back and we'll go over this problem. And then we're going to cover sections 5.8 and 5.11, which are the last 2 sections that we cover in this chapter.